One relatively common situation for first-order differential equations is to have a differential equation where the independent variable doesn't actually show up at all, like this differential equation, right? Usually we expect first-order differential equations to have a function of x and y on their right-hand side, but for this particular differential equation, it's only y that shows up in this function. This sort of differential equation is called an autonomous differential equation because it's autonomous from x, I guess, autonomous from the independent variable. And this sort of equation has a few tricks associated with it. One nice thing about this sort of differential equation is, let's ask ourselves, what happens if by some coincidence we happened to have dy dx being 0? Well, if dy dx were 0, then y would not change, because after all its derivative is 0. And if y isn't changing, that means, right, the dy dx is only a function of y. So if a particular y value makes this 0, then y doesn't change, and this derivative keeps being 0. So it stays 0. So then we would have a solution just at that particular y value. This is called an equilibrium solution. Because it doesn't change. So we can find an equilibrium solution just by solving this equation. So for our particular differential equation, dy dx equals y minus 1, if we set this equal to 0, we can solve for y. Just add 1 to both sides. And you get y equals 1. And this is a solution to the differential equation. We can check the solution to the differential equation just by plugging it back into the original differential equation, which was dy dx equals y minus 1. Well, the derivative of y is 0. And if we plug y and its derivative into this equation, we get 0. Is this equal to y, which is 1, minus 1? Yeah, that checks out. So we found a genuine solution. Now, we have only found one solution, and just because of our existence and uniqueness theorem, we can tell that there should be solutions for every initial condition. And if we graph our solution, we have only found a constant solution through the y value 1. So there are lots of other solutions, but we don't know what they are right now. The only thing we can tell about them is that they aren't constant, because if they were constant, we would have found them because they would be equilibrium solutions. If we wanted to find other solutions, we'd either have to do some other calculation or draw a direction field to get some idea of what they look like. All right, well, let's use this idea to find equilibrium solutions for this differential equation. So this is an autonomous differential equation because x does not show up on the right-hand side of this differential equation. And even before we start, the right-hand side of our differential equation, which is y squared minus 4, it's continuous on the entire xy plane, and its derivative with respect to y is 2y, and that's continuous on the entire xy plane. So we're going to have solutions that exist for every initial condition, and we also are going to have unique solutions for every initial condition. Okay, with that in mind, let's go ahead and find the equilibrium solutions. To find the equilibrium solutions, we just set this equal to 0 and then solve. So y squared is 4, and that means y is plus or minus 2. So if we wanted to graph these, we know at y equals 2 and y equals minus 2, we have solutions that just stay the same all the time. All right. Now, you can see because x doesn't show up in this equation, this picture that we've drawn it kind of has a lot of extra information. All we really needed to draw to sort of make a picture of what we know about this differential equation is just the y-axis. Right? So we have an equilibrium solution at 2, and we have an equilibrium solution at -2. Now, for y values, this is the y-axis. For y values away from 2 and -2, we don't have equilibrium solutions, but what we could do is figure out what is this derivative doing in each region. So you see these equilibrium solutions sort of break the y-axis up into chunks, into these 3 chunks. Bigger than 2, between -2 and 2, and less than 2. And if we look at the part, say, where y is bigger than 2, let's pick just some y value in here, maybe 3. So dy dx when y is 3, right, we can plug 3 into our differential equation, and we get 9 minus 4, that's 5. That's bigger than 0. So if a solution started out above 2 here, its derivative would be positive, and that would mean that it would increase. So if we start at a y value larger than 2, we continue increasing because dy dx is positive. Okay, what about if we start at a y value between -2 and 2? Let's check, how about y equals 0? When y is 0, dy dx is -4, and that's less than 0. So if we start between -2 and 2, then the y value is decreasing. So if we start anywhere in here, we decrease. And then finally, we could try in this bottom region. Let's use maybe y equals -3. We would get 5 again, and that's positive. So if we started below y equals -2, we would increase like this. This picture that we've drawn actually gives us sort of a quick impression of what solutions are going to do no matter where you are in the y direction. So this is sort of a nice summary of how solutions behave. Notice that we haven't actually solved to find solutions, but we know generally what the solutions are going to do, how they're going to move around the xy plane. So this picture is called a phase portrait. Or because this phase portrait happens to just be one-dimensional, sometimes it's called a phase line. Having a phase portrait gives us a couple of nice pieces of information. So one is we can actually sketch solutions using our phase portrait. So we know if we're above y equals 2, we're going to increase. So that would be like this. And as you run time back, as you run your x value to the left, of course, if your slope is positive, that means you're decreasing as you go to the left. And we could do that for other initial conditions above y equals 2. Say over here, maybe. It would look like this. And as we go to the left, it has to decrease. But remember, since we have unique solutions, we can't have solutions crossing. So as the solution we're sketching moves to the left, it can't cross the equilibrium. It has to sort of squeeze in there. And like this. Okay, between -2 and 2, we could sketch a solution. Maybe we could sketch the solution that starts at the origin. Between -2 and 2, we know that solutions are going down, because that's what our phase portrait says. So our solution has to head downwards. But remember, because solutions are unique, we can't cross this equilibrium solution at -2, so our solution must sort of level out. So it's still decreasing, but it never actually gets to this equilibrium at -2. And of course, when we run things to the left, it all happens in reverse. We increase and have to level off so that we don't cross the equilibrium solution at +2. If you start at other points between -2 and 2, the same general thing kind of happens, like this. Okay, and then finally, if you started below -2, right, our phase portrait says that below y equals -2, solutions should be increasing, so that would look like this. And again, we can't cross that equilibrium solution at -2, so our solutions kind of bunch together as you move to the right. So that's one nice thing that a phase portrait lets you do. It gives you a quick way to sketch what solutions are going to look like. Now, if you look at these two equilibrium solutions, the one at y equals 2 and the one at y equals -2, they actually have a very different character. The equilibrium solution at y equals 2, as x increases, solutions nearby this equilibrium are sort of driven further away. Right? And we can see that on the phase portrait as well. If you start a little bit above y equals 2, you go further up. And if you start a little bit below y equals 2, you go further down. So this equilibrium at y equals 2 is driving other solutions away from it. So it is an equilibrium, but if you step off of the equilibrium, you end up further and further away. So this is called an unstable equilibrium, because it is an equilibrium, but as soon as you step off just a tiny bit, you get forced further and further away. This is very different to the equilibrium at -2, because if you imagine starting somewhere just nearby the equilibrium at -2, you get forced further and further towards the equilibrium at -2. And that's true whether you start above or below. So the equilibrium at y equals -2 is called stable. So this is a stable equilibrium. And we can see that on the phase portrait as well. If you start a little bit above -2, this red arrow is forcing us back down. And if you start a little bit below -2, we're being forced back up towards the equilibrium. So your phase portrait, it lets you sketch solutions, and also it lets you classify equilibrium as stable or unstable. Of course, stable drives things away on both sides, and stable draws solutions closer on both sides, and unstable equilibria drive things away on both sides. You might wonder, is it possible for an equilibrium to draw solutions closer on one side but drive them away on the other? And that is possible. That's what's called a semi-stable equilibrium. So just to see how that works out, let's sketch a phase portrait and some solutions for this differential equation, dy dx equals y squared. Our existence in uniqueness theorem does guarantee that we will have unique solutions for all initial conditions for this differential equation, because it's continuous everywhere, and df, our partial f partial y, is 2y, and that's continuous everywhere in the xy plane. So let's find equilibrium solutions and sketch a phase portrait. To find equilibrium solutions, we take the right-hand side of our equation, set that equal to 0, and solve for y, and we get just one equilibrium solution at 0. So sketching our phase portrait, we can put our equilibrium at 0. This breaks the y-axis up into two chunks, the positive and the negative. So to know in each chunk whether solutions increase or decrease on that portion, we could just either think about what y squared does, or we could plug in a test value. So we could plug in y equals 1. So dy dx at y equals 1 is 1, and that's bigger than 0. And so on the interval greater than 0, solutions increase. And we could do the same thing for a negative y value. How about -1? And for this y value, the dy dx comes out to be +1 again. And that's bigger than 0. And that means for negative y values, any solutions that start with negative y values increase. So our phase portrait would look like this. And you can see on one side, just above our equilibrium at 0, solutions get forced further upwards. And on the other side, just below the equilibrium at y equals 0, solutions get drawn closer to the equilibrium. And so this is that mixed case where it's not stable or unstable, and this is called semi-stable. If we wanted to sketch what solutions would look like on the xy plane near this semi-stable equilibrium, first let's draw our equilibrium at y equals 0. So there's our equilibrium. If we start just above our equilibrium, right, our phase portrait says that solutions will increase further, so that would be like this. And of course, as we go to the left, they have to decrease. But of course, because of uniqueness of solutions, the solution we're sketching can't cross the equilibrium solution. And if we started below the equilibrium, the phase portrait says we have to increase. So that would look like this. And as usual, we can't cross the equilibrium solution, so we get something like that. And as we go to the left, it plunges downwards, so something like this. So that's what a semi-stable equilibrium looks like. All right. Now, one other nice thing we can do with this idea of an autonomous equation is to produce a differential equation that has equilibria that we want. This is sort of a handy trick to have up your sleeve if you have some physical situation where you know what the equilibria are and you know how solutions should increase or decrease, but you don't have any sort of full-blown knowledge about the system that lets you write a more specific mathematical model. So let's write a differential equation that has a stable equilibrium at y equals 5 and an unstable equilibrium at y equals 1. So we know that, right, we're going to write a differential equation dy dx equals f of, I didn't say this, but I guess we can insist that it be an autonomous differential equation. And we know that to produce these equilibria at 5 and at 1, we know that f of 5 had better be 0. And we know that f of 1 had better be 0. This will produce equilibria at 5 and at 1. So we just need to come up with some function that has zeros at 5 and 1. And, you know, polynomials are a nice class of functions where it's easy to specify what the zeros are. So we can have a 0 at 5 if we put y minus 5 in here, and we can have a 0 at 1 if we put y minus 1 in here. Okay, so let's see how this works, or let's see if this works. Just because of where the zeros are, we know that we have these two equilibria, but if we multiplied this out, we get y squared minus, I guess, 6y plus 5. And if we check some test points to complete this phase portrait, let's see, we could check 6 and 2 and 0. So I'll let you do the calculations, but it turns out that the phase portrait comes out like this. It's up at the bottom, it's down in the middle, and it's up at the top. So for this differential equation that we've written down, the equilibrium at 5 is unstable, and the equilibrium at 1 is stable. And that isn't what we wanted. So we have the correct equilibria, but they don't have the right stability, right? But there's a nice way to switch these. Just because we have the stability backwards, right, all we need to do to fix this is make what was positive negative and what was negative positive. So just throw a minus sign in front of it. And now if we redraw the phase portrait, I won't go through all the steps, but if we redraw the phase portrait, work out some sample points, the phase portrait comes out like this. Down at the top, up in the middle, down at the bottom. And that does give us an unstable equilibrium at 1 and a stable equilibrium at 5, just like we wanted.